Welcome to another deep dive. Today we're going to be tackling something that might sound a little familiar,
Mhm.
but trust me, we're going way beyond the basics here.
Oh, yeah.
We're going to be diving into the world of quadratic equations.
Yeah.
You might be here to brush up for a class, or maybe prepping for a technical interview, or even just out of pure curiosity.
hmm
But get ready, because we're about to uncover the core concepts of these equations and maybe even reveal some surprising connections that you might not have thought about before.
Yeah, that's what's so cool about quadratic equations, right? It's that they're not just some abstract math concept. You actually see them everywhere.
Oh, yeah, for sure.
Like you said, from physics to engineering to economics and even computer graphics.
It's amazing.
Understanding these equations just opens up a whole new way of thinking about the world around us.
All right, so let's get into this. The material that we're looking at dives right into this idea of quadratic expressions,
hmm
which I remember from back in the day, something like x squared plus bx plus c,
Yeah.
where a can't be 0.
hmm
And then it goes on to define a quadratic equation as setting that entire expression equal to 0.
Right.
Why is that little difference so important?
Well, yeah, it is subtle, but it is really important, right? So that expression is just a relationship, like a mathematical recipe, if you will.
Okay.
But when you set it equal to 0, it's like you're asking this question.
Ooh, okay.
What values of x will make this whole thing equal 0?
Mhm.
And finding those values, the roots, it opens up a whole world of problem solving.
Yeah, and it even emphasizes that, like, finding the zeros of a quadratic expression is the same exact thing as finding the roots of the equation.
It is, yeah.
And that quadratic equation always has two roots.
Exactly.
But wait a minute, what about, you see these parabolas sometimes that never even touch the x-axis.
Yeah.
How can they have roots if they never hit 0?
Oh, man. This is where it gets interesting.
Okay.
This is where we get into the realm of imaginary roots. They might not show up on a standard graph, but mathematically they're there. We can even calculate them.
So they involve, like, imaginary numbers.
Exactly, yeah. They involve the square root of -1, which is represented by I, and it sounds kind of, abstract and out there.
Yeah.
But these imaginary roots actually have real-world applications.
Wow.
Think about things like electrical engineering or quantum mechanics. Those are areas where imaginary numbers and these imaginary roots actually come into play.
That's wild.
So, yeah, even when we can't see those roots on a graph, they're still there, working behind the scenes.
That's so cool.
Right.
So just to kind of sum all this up for everyone listening, a quadratic equation is an equation of the form x plus bx plus c equals 0, where a, b, and c are constants. A is never 0.
Hmm.
The zeros of the quadratic expression, those are the values of x that make the expression equal 0, and those are also the roots of the equation. And these roots can be real or imaginary, but a quadratic equation will always have two of them.
Always. Absolutely.
Now, the source material goes on to give us this formula, the quadratic formula, to directly solve these equations.
Mm-hmm.
And I'm not going to lie, it looks kind of intimidating.
It can be, yeah. It's a bit of a mouthful.
Is it really as complicated as it looks at first glance?
I mean, the formula itself might seem complicated, but honestly, the beauty is that it always works. No matter what the values of A, B, and C are, you can just plug them in and it spits out the two roots, whether they're real or imaginary. And within that formula, there's this special piece called the discriminant, which is b squared minus 4ac. And this little gem tells us a lot about what those solutions are going to look like.
Okay, so what does the discriminant actually tell us? How does knowing b squared minus 4ac help us understand those solutions?
Think of it like a code embedded within the formula.
Okay.
So if the discriminant, this b squared minus 4ac, if it's positive, then we know we're going to have two distinct real roots. That means the parabola, that U shape that represents the expression, it crosses the x-axis at two separate points.
Okay.
But if the discriminant is 0, then we have two real roots, but they're identical.
Oh, okay.
So the parabola just grazes the x-axis just at one single point.
Hmm.
And now here's where it gets really interesting. If the discriminant is negative, that's when we have those fascinating imaginary roots.
So it's like a little sneak peek into what kind of roots we're dealing with before we even go through and solve the entire equation.
Absolutely. It's a little preview of the nature of the solutions.
That's so cool.
Just so everyone listening is on the same page, the quadratic formula is x equals -b plus or minus the square root of b squared minus 4ac, all divided by 2a. That gives you the solutions, the x values, to a quadratic equation. And remember, the discriminant, which is often represented as just a capital D, is just that b squared minus 4ac part. And that helps us figure out whether those roots are real and different from each other, real and the same, or imaginary.
This is already shedding so much light on these equations. Now, the source material goes on to talk about how the roots of a quadratic equation are related to the original coefficients, the a, the b, and the c.
Yeah.
What's the big takeaway there?
Well, this is where I think the elegance of math really shines through. The sum of the roots and the product of the roots, they have these beautiful, predictable relationships with those coefficients. Specifically, the sum of the roots will always equal negative b over a, and the product will always equal c over a.
So even without knowing the roots themselves, we can get information about them just from those coefficients.
Exactly.
That's super helpful.
It is.
Could we, for example, use these relationships to, I don't know, like quickly double check if we solved an equation correctly?
Absolutely, yeah. If you solve a quadratic equation and you find your two roots, just add them together, see if they equal negative b over a,
Okay.
and then multiply them together, see if that equals c over a.
Oh, that's brilliant.
It's a really great way to catch any mistakes you might have made along the way.
So it's like a mathematical safety net.
Exactly.
That's amazing.
Just to make sure everyone's got this. For a quadratic equation of the form x plus bx plus c equals 0, the sum of the roots is always going to be equal to negative b divided by a, and the product of the roots is going to be equal to c divided by a.
All right. And now the source material kind of takes us into this slightly more abstract realm.
Okay, yeah.
It talks about transforming a quadratic equation,
Uh-huh.
basically creating a new equation, but whose roots are related to the original equation's roots in some way. Why would you ever want to do that? That
Right.
sounds kind of weird.
It might sound abstract, but imagine, like, you're dealing with a system that's modeled by a quadratic equation. Maybe it's like the trajectory of a rocket or the behavior of a stock market trend or something like that.
Oh, okay.
And you need to adjust that system somehow, like shift the trajectory or maybe accelerate the trend. By transforming the equation, you can essentially make those adjustments indirectly. It's kind of like fine-tuning a machine by like adjusting its internal gears or something.
I see.
You're manipulating the roots without having to directly change the original equation itself.
Can you give us a simple example from the source material to kind of illustrate how this transformation works?
Sure, yeah. Imagine you have an equation and its roots are 2 and 3.
Okay.
And you want to come up with a new equation, but where the roots are double those original ones.
So 4 and 6.
Exactly, 4 and 6. The source material actually walks through the steps of how you would do that.
Wow.
It's really quite fascinating. It's almost like a form of mathematical alchemy.
That's amazing. So for our listeners who want to go a little deeper into this, transforming a quadratic equation is basically finding a new equation whose roots are some function of those original roots.
Right.
And you do this by expressing the original roots in terms of the new roots that you want, and then substitute those expressions back into the original equation. It's like you're messing with the very essence of that equation.
You are. You're changing its fundamental building blocks.
That's really cool. Now, the source dives even deeper into the nature of roots, talking about whether they're real or imaginary, rational or irrational, all that good stuff. And it also gets into using inequalities to define regions where a quadratic expression is positive or negative. This feels like we're gaining some serious X-ray vision into the behavior of these equations.
Yes, absolutely.
But what's the practical value of all this? How does this translate to actually solving problems in the real world?
Well, think of it this way. Understanding the nature of the roots and being able to analyze inequalities, it gives you the ability to predict how these equations are going to behave under different conditions. It's like having a crystal ball, but for quadratic equations.
Okay, I like that.
Yeah.
So how does the source material use the discriminant to figure out the nature of the roots? And how do those inequalities come into play?
It all ties back to that discriminant that we talked about, the b squared minus 4a.
Right.
Remember, if it's positive, we get two distinct real roots. 0 gives us two identical real roots,
Right.
and negative gives us those imaginary roots. But we can actually take it a step further than that. We can even use the discriminant to figure out if those real roots are rational or irrational. It all comes down to whether the discriminant is a perfect square or not.
Wow.
As for inequalities, those allow us to define, like, regions on the number line where the quadratic expression is either positive or negative. For example, we can figure out for what range of x values the parabola is sitting above the x-axis.
So it's like we can really see where this equation lives and breathes, so to speak.
Exactly. We're not just finding specific solutions anymore. We're understanding the entire landscape of that equation.
This is really cool. But can you give me a concrete example of how somebody might actually use inequalities with quadratics in a real-world scenario?
Sure, yeah. Imagine you're an engineer and you're designing a suspension bridge. The curve of those cables holding up the bridge, that can be modeled by a quadratic equation.
Wow.
To make sure the bridge is safe, you want to know the sections where those cables are above a certain height.
Right, yeah, of course.
To figure that out, you would set up a quadratic inequality, and then you would solve for the range of, in this case, distances along the bridge where the cables satisfy that height requirement.
That's an incredible application.
Yeah.
So to kind of clarify these concepts for everyone, the nature of roots, that refers to whether the roots are real and distinct, real and equal, or imaginary. And then inequalities, those are used to figure out the range of x values, where the quadratic expression meets a certain condition, like being positive or negative.
Exactly. It's about understanding the big picture, not just the specific solutions.
Okay, that makes sense.
All right, feeling good about this so far?
This is already blowing my mind a little bit.
I know, right? Quadratic equations are pretty wild.
And just when I thought we were reaching the peak of our quadratic equation adventure,
Yeah.
the source material drops one more fascinating concept on us. Locating roots. What does that even mean? Like, how can you find where the roots are without actually solving the equation?
It's almost like a superpower, right?
Yeah.
Locating roots is all about using clever analysis and a deep understanding of how quadratic equations work to figure out where those roots live on the number line without having to go through the whole process of solving for them directly.
That's wild. So it's like having a map that tells you where the treasure's buried without giving you the exact coordinates.
Exactly. It just gives you a general idea of the location.
I'm intrigued. But why wouldn't we just solve the equation and get those precise answers?
Well, sometimes, you might be dealing with an equation that's really complicated and finding the exact roots would just be a huge headache.
Oh, I can imagine.
Or maybe in a real-world situation, a rough estimate is good enough.
Okay.
So in those cases, locating roots can save you a lot of time and effort while still giving you valuable information.
So it's kind of a way to get a sense of the quadratic equation's behavior without getting bogged down in the nitty-gritty details.
Exactly, like understanding the big picture.
Yeah.
And the source material actually describes several really neat techniques for doing this.
Oh, cool. So what kind of techniques are we talking about here?
One involves checking the sign of the quadratic expression at different points. So let's say you plug in one value for x and you get a positive result. Then you plug in a different value for x and you get a negative result. That tells you that somewhere between those two x values, that expression must have crossed 0, meaning there's a root hiding in that interval.
So it's like we're following the trail, looking for those clues that lead us to the root.
Precisely. We're playing detective with the quadratic equation.
I like it. Are there any other techniques?
Yeah, we can also use those relationships between the roots and the coefficients that we discussed earlier. So for instance, if we know that the sum of the roots is positive, but their product is negative, then we can figure out that one root must be positive and the other one must be negative.
So we can use logic and deduction to narrow down the possibilities.
Exactly.
I like that. Is there any one technique from the source material that you find particularly elegant or effective?
One that I find really cool is the idea that if a quadratic expression changes its sign between 2 points, like we were just talking about, then at least one root has to be lurking between those points. It's a very simple concept, but it's so powerful for understanding where those roots are without having to do a bunch of complicated calculations.
So just so our listeners are clear on this, locating roots means figuring out where the roots of a quadratic equation are on the number line, but without having to actually solve for those exact values.
Right.
And we can do this by analyzing the sign of that quadratic expression at different points, using the relationship between those roots and the coefficients, and remembering that a change in sign means a root is hiding somewhere nearby.
You got it.
This is incredible. We've already covered so much in this deep dive, from the basic definition of quadratic equations and all the way to this idea of locating roots without even solving them directly.
Yeah, and the best part is we're just getting started.
I can't wait to see what other secrets these quadratic equations have in store for us.
Oh, there's plenty more to uncover, trust me. Welcome back to our deep dive on quadratic equations. Last time we laid a lot of the groundwork, exploring the quadratic formula, the discriminant, and even touched on those fascinating imaginary roots.
Yeah, that was pretty mind-blowing.
But now it's time to, put all these concepts into action and see how they can help us solve real-world problems.
I'm excited to see those abstract ideas come to life. So the material dives into an example that involves quadratic equations that have roots that are equal in magnitude but opposite in sign.
Right.
That seems like a very specific scenario. Why is that case highlighted?
Well, it's all about recognizing patterns and shortcuts. When you encounter a quadratic equation and you know that the roots have that specific property, equal magnitude but opposite sign, you automatically know something about the equation itself. You know that the coefficient of the x term, that middle term, has to be 0.
Ah, so it's like a secret code. If we spot that pattern, we instantly unlock a piece of the puzzle without having to solve the whole thing.
Exactly. It's a quick and elegant way to simplify the equation.
I love those kinds of shortcuts.
Yeah.
Are there any other special cases like that we should be on the lookout for?
Absolutely. The material highlights a few more. Like, for example, if one of the roots of a quadratic equation is 0,
Okay.
then you immediately know that the constant term, the c in our equation, also has to be 0.
Wow.
These shortcuts can be super helpful when you're trying to solve problems and you want to get a deeper understanding of how these quadratic equations are structured.
Definitely adding those to my math toolbox. All right, let's talk about graphs. The material goes into quite a bit of detail about how the graph of a quadratic expression, which is always a parabola, how that graph changes based on the values of a, b, and c and the nature of the roots. It even categorizes these parabolas into 6 different types. Why is it so important to understand these visual representations of the equations?
Well, I think graphs are like windows into the world of math. They give us a visual way to grasp what the equations are actually telling us. And for quadratic equations, those graphs, those parabolas, tell us a lot about the roots, the vertex, the axis of symmetry, all that good stuff.
So by just looking at the graph, we can actually tell whether the roots are real or imaginary, or if they're distinct or equal, or even if they're positive or negative.
You got it. Each of those 6 categories of graphs represents a different scenario. So, for example, if your parabola intersects the x-axis at 2 different points, you know you've got 2 distinct real roots.
Okay.
If the parabola just touches the x-axis at its vertex, that's when you have 2 equal real roots.
Makes sense.
And if the parabola never intersects the x-axis at all, well, that's when we know we're dealing with those imaginary roots.
So it's like the parabola's whispering secrets about the equation it represents.
Exactly. The shape of the graph tells the story.
I love how a visual representation can really unlock that understanding. Now, the material mentions something interesting. It says that if a is greater than 0 and the discriminant is less than 0, then the quadratic expression is always positive. What does that mean visually in terms of the graph?
That's a great observation. It means that the parabola opens upwards, kind of like a smile. And because the discriminant is negative, we know we have those imaginary roots. So what that means is that the entire parabola is sitting above the x-axis. No matter what value you plug in for x, you're always going to get a positive result.
So it's like the parabola is floating above the x-axis, never actually touching it.
Exactly.
Almost like those imaginary roots are holding it up in the air.
Okay.
So we've talked a lot about quadratic equations themselves, but the material then introduces the concept of quadratic inequalities.
Yeah.
How do those differ from equations, and why is it important to understand them?
Yeah, so while equations ask us to find the specific values of x that make an expression equal to something, inequalities broaden our perspective a little bit. They allow us to consider a whole range of x values that satisfy a particular condition.
Oh, okay.
So instead of just pinpoint solutions, inequalities give us regions of solutions. Like an inequality might ask, for what values of x is this expression greater than 0? Or for what values of x is this expression less than 5?
That seems incredibly useful for real-world applications where we might have constraints or tolerances. Can you give me an example of how we might use quadratic inequalities in a practical scenario?
Sure. Imagine you're a physicist studying the trajectory of, say, a basketball being thrown towards a hoop.
Okay.
The height of that ball over time, that can be modeled by a quadratic equation.
Right.
And let's say you want to know the time interval during which the ball is above a certain height, like the height of the basketball net. To find that out, you'd set up a quadratic inequality, and then you'd solve for the range of times that satisfy that condition.
So instead of just knowing the exact moment the ball reaches a specific height, we'd know the entire window of time when it's above the net.
Exactly.
That could be super helpful for analyzing a shot, for example. Now, the material goes into different techniques for solving these inequalities, like factoring, graphing, test points, all that good stuff. What's the most important thing for our listeners to keep in mind when they're tackling these kinds of problems?
I think the key is to remember that solving inequalities is all about finding those regions on the number line where the expression meets a specific condition. And often that means breaking down the problem into different cases, considering the sign of the expression in those different cases, and then carefully testing values to make sure you've got the right solution set.
Okay, so it's like a bit of a detective game.
Yeah.
Carefully examining all the evidence to piece together the solution. I like that.
That's a great way to think about it. Now, the material goes on to introduce a specific type of inequality called an irrational inequality.
Irrational inequality. Okay. What makes them irrational, and how do they differ from the quadratic inequalities we've been talking about?
So irrational inequalities, they involve expressions that have radicals in them, like square roots or cube roots.
Okay.
And those radicals, they add a little bit of complexity because we have to be super careful about the domain of those expressions. Remember, you can't take the square root of a negative number.
Right.
So we need to make sure that the expression underneath that radical sign is always non-negative.
So when solving these irrational inequalities, we have to consider those domain restrictions to make sure we're not breaking any math rules.
Precisely.
Seems like those require extra caution. So to be clear for our listeners, irrational inequalities are inequalities that involve expressions containing those radicals, like square roots or cube roots. And when solving them, it's crucial to remember those domain restrictions, making sure that the stuff under the radical is never negative.
Well said.
All right. Moving right along, the material mentions another type of inequality called a modulus inequality. What are those, and how do they connect back to our friend, the quadratic equation?
Yeah, modulus inequalities. They involve the absolute value of expressions. So remember, the absolute value of a number, it's just its distance from zero, regardless of whether it's positive or negative.
Right.
So these modulus inequalities often lead to situations where we have to consider both the positive and negative versions of the expressions that are involved.
So it's like we're looking at the expression, and its mirror image on the other side is zero.
Exactly. You've got it. Now, the connection back to quadratic equations is that sometimes when you're working with these modulus inequalities, you might end up with quadratic expressions inside those absolute value bars.
Okay.
So that means we need to combine what we know about quadratic equations and absolute values to find the solution.
It's like we're layering these different mathematical concepts on top of each other, using our knowledge of each to solve increasingly complex problems. I like it. Just for clarity, can we define modulus inequalities for the listeners?
Sure. Modulus inequalities are inequalities that involve the absolute value of expressions. And like we said, they often require us to think about both the positive and negative versions of the expressions to find the complete solution.
That's a great summary. Okay, we've already covered so much ground, but the material has even more to reveal, right?
Oh, yeah, definitely.
Where do we go from here?
We're about to explore one of the most practical and powerful applications of quadratic equations. Finding the maximum and minimum values. This has huge implications in fields like optimization, physics, finance, all sorts of areas.
All right, let's unlock those optimization secrets. I'm ready. All right, so we're back for the final part of our deep dive into quadratic equations. We've gone through the quadratic formula, encountered imaginary roots, explored those inequalities, even seen how these equations look visually as graphs.
Yeah.
But now we're going to unlock one of the most practical applications, right? Finding those maximum and minimum values.
Yeah, exactly.
This has real-world implications in fields like optimization, physics, finance, all sorts of things. But before we dive into that, we've been talking a lot about parabolas, which are the visual representations of those quadratic equations.
Right.
I'm guessing those maximum and minimum values have something to do with the vertex of that parabola.
They got it. The vertex is the key to understanding those maximums and minimums. So think about a parabola, right? It can either open upwards, kind of like a bowl, or downwards like a hill. The vertex is that special point, either at the very bottom of the bowl or the very top of the hill.
Okay. So if the parabola opens upwards, the vertex represents the minimum value, and if it opens downwards, that vertex is the maximum value.
Exactly. You nailed it.
Cool. But how do we actually find that vertex?
Well, there's a handy little formula that gives us the x-coordinate of the vertex.
Okay.
It's negative b over 2a, where b and a are those coefficients from our quadratic expression x plus bx plus c.
Right.
Once we have that x-coordinate, we just plug it back into the expression to find the corresponding e-coordinate. And boom, there you have it. The coordinates of the vertex, which also tells you the minimum or maximum value.
It's amazing how such a simple formula can give us that critical information. Now, does the discriminant play any role in figuring out this maximum or minimum value?
It doesn't directly tell us the maximum or minimum value itself, but it does tell us whether that parabola intersects the x-axis or not, which influences the nature of that maximum or minimum. So if the discriminant is positive, meaning we have two distinct real roots,
Right.
the parabola crosses the x-axis, which means the vertex will be a minimum point if the parabola opens upwards or a maximum point if it opens downwards.
Got it.
But if the discriminant is negative, meaning we have those imaginary roots, the parabola never actually touches the x-axis. In that case, the vertex is still the minimum or maximum, but the expression itself never actually equals zero.
So the discriminant helps us see that bigger picture, how the parabola behaves, and that gives us insight into what kind of maximum or minimum we're dealing with.
Okay, this is all making sense. The material discusses a special case where the quadratic expression is a perfect square. What's so special about this scenario?
When you have a quadratic expression that's a perfect square, its graph, the parabola, just barely touches the x-axis at a single point.
That means the discriminant is zero, and the two roots are identical. And the vertex of the parabola is that single point where it touches the x-axis.
So for a perfect square, the vertex is the only point where the expression equals zero.
That's interesting. But let's shift gears a little bit. The material introduces this idea of finding maximum and minimum values, but now for rational algebraic expressions. So those are expressions involving fractions where both the numerator and the denominator are polynomials.
Right. Yeah.
How do we approach these optimization problems when we're not just dealing with a simple quadratic expression anymore?
It does get a bit more complex, but the fundamental principle is the same. We're still looking for those highest and lowest points on the graph. But now, instead of a simple parabola, we might have a graph with like more intricate shapes, maybe some asymptotes, multiple turning points, things like that.
So the visual intuition of finding the peaks and valleys still applies, but the process of actually finding those points might be a bit trickier.
Right. It can be a bit more involved. What strategies does the material suggest for dealing with those rational algebraic expressions?
It lays out a pretty clear step-by-step approach. You start by setting that rational expression equal to a variable like y. Then you cross-multiply and simplify everything to get a quadratic equation in x.
Okay.
And from there, you can use what you know about the discriminant and inequalities to determine the range of possible values for y, which represents the range of that original rational expression.
So we're kind of cleverly transforming a rational expression problem into a quadratic equation problem, something we've already learned how to tackle.
Exactly. We're using the tools we've developed to solve a new type of problem.
I like that. All right, we've covered so much in this deep dive. We explored all those fundamentals of quadratic equations, the quadratic formula, the discriminant, graphs, inequalities. We even talked about imaginary roots, which was pretty wild.
It's a lot to take in, for sure.
We've seen how to solve these equations, how to graph them, how to manipulate them, even how to find those roots without actually solving them directly.
Yeah, it's all about building that intuition and understanding the different ways we can approach these problems.
And it's all thanks to the amazing power of mathematics.
Absolutely. Math is more than just memorizing formulas. It's a way of thinking.
It's a language that allows us to understand the world around us, to describe patterns, to make predictions, to solve problems.
I couldn't have said it better myself.
Quadratic equations are just one small piece of that vast mathematical puzzle, but understanding them opens up a whole world of possibilities.
And there's always more to explore.
Always something new to discover.
Exactly.
So to everyone listening, keep exploring, keep questioning, keep pushing the boundaries of what you know. You never know what fascinating mathematical adventures await.
Well said.
Thanks for joining us on this incredible deep dive into quadratic equations. Until next time, keep diving deep into whatever sparks your curiosity.